what I would like to talk about is something that may be a little bit foreign to some of you here, which is static typing. And what I really want to do is to show a proper static typing system which lets us really do some interesting things and isn't just like the typing system in languages like C or Java, which just gets in the way. But I hope what I can show today convinces you that there is actually something here that can help you write better software and which makes you interested in what static typing can do for you. So what I first would like to know is, anyone here in the audience who has had some experience with the languages like Haskell or OCaml or something? Maybe show of hands. Okay, how many of you who showed your hands has actually written running useful software in one of those languages? Okay, not that much, which is good, because I want to convince you that this is actually possible. I can show you some things later which have been done. I would like to start at the very beginning. What is actually going on here? What I've started doing here is the first 3 lines you can ignore. That's a little bit of ceremony. I just initialized a module, gave it a name, and then imported the standard library and basically excluded most of it because I want to show how some things in the standard library that Haskell usually comes with are implemented and how the inner gears of Haskell work a little bit. So line number 5, I just defined a simple data type. The data type models playing cards, so I have a data type which is called Karte, and I have 6 different cards that are in my playing set, which are delimited by those pipe signs. So these are very simple type with very simple values. At the end, the deriving show just means that I want Haskell to figure out for itself how this data type should be printed on the command line, so I don't have to bother about that. The first function I have defined here is called Kartenwert, and the only thing that this function does is it takes a card and looks up what card is it and returns a numerical value for that. This doesn't have anything to do with actual card playing. It's just for demonstration purposes. What we can see here in the first line is the number of the function, 2 colons, and then the signature of the function. And this is something that you will see all the time in my demonstration. You can actually leave that out. In most cases, modern compilers like the GHC are able to figure these things out for themselves. I like to write these signatures at least for top-level functions, simply because it supports the developer. When I look at a function signature, it tells me much about what the function actually does. So this function takes a card and returns an integer, and the lines that come after that, you see the typical way how I define a function, what a function actually does. I have the function name, and after the function name I have what is called a pattern. I do pattern matching, and I basically just listed the values that I can expect here, and after the equal sign there is the actual function definition, which are just simple integers in this case. So this is the very most simple example that I could come up with. It's contrived, but it's just for demonstration purposes. Now, how would I go on and say, well, for for a set of playing cards, maybe there is a collection of cards that I hold in my hand and I want to model that in some way, in some form of list. I can do that very simple and call this my hand. I give this little hyphen at the end of it to signify that this is some variation of the data structure hand. I will define other variations of this later on, which are more generalized. And basically I can have two different cases here. Either my hand is empty, maybe I can even type it correctly, or non-empty, and in the case it is non-empty, I actually need to have at least one card and the rest of my hand. So this is the most simple case, which some people may know data structures like this, like linked lists in languages like C. What's interesting about these data structures, they are defined in a recursive way, and we can write functions recursive that iterate over these data structures. So we can handle these data structures really well and nice. And what I would like to know is, when I have my my hand, a list of cards, how much are these cards worth in sum? And I can write a more or less simple function for that, which takes my my data structure, which I call hand, and returns again an integer. And now is the question, okay, what kinds of values can I expect to get for this function? Well, the first value I can expect would be empty. And an empty hand, I just say, has the value 0. So I get some kind of base. 0 is the neutral element for sums. And the other thing that can happen is that my hand is non-empty, and in this case, I have accompanying this non-empty value first a card, which I assign the variable k, and I have the rest of the cards, which I call ks. And then I basically say, okay, what might this be worth? And first I'd say the value of k, and add to that the rest of the value of the rest of the cards that I have in my hand. Does this make sense? Is this something that that people can understand? I will see. Yes, it type checks. Very good. So what I can now do is have I actually, yes, this is the right code. I reload this the source file that I edited just now. And this is an interactive environment which is called GHCI, so I can work with my code without always compiling it into a binary and do all these different steps. And yes, the first thing that I would like to define is just some simple hand where we have non-empty. Let's say we have an ace, and I define them in German, so I have to type them in German, and maybe something like that. So I see this data structure. Usually lists are defined with a little bit of syntactic sugar, so I don't have to explicitly do all this typing, but I wanted to show how these work internally, and therefore a little bit more verbosity is better for explaining all this. And now I can take my function, give a function this hand that I just defined, and it should give me a number, which is 8. Let's see, I have an ace and 8 and a jack, and this is a 1 and 2 are 3, and an ace is 5. This seems to be correct, which is nice. Live coding works. Okay, I defined a linked list which just accepts these cards which I just defined. This is not very flexible. I don't want to implement linked lists for every single data type that I define or that is that Haskell has internally. So I want to have some sort of saying, okay, I have a linked list, and this linked list has data of some variable type. And the way I do this is I can simply define a list of type A. And this means I have the type list, but list is not the complete type. List takes another type, which makes the complete type the final type. And this variable A is this additional type that the type constructor list expects. And I also have two cases, and I use the default names, which maybe which some people may know from Lisp if they use that. And I have either nil to say it's an empty list, or I have the cons case, which takes a value of type A and a list of type A. This ensures that every single value in this list is of the same type, but every list that I construct can have a different type. And I want derive show so that we can actually see anything. And now I can do one thing. Usually I have these really flexible data structures that come with Haskell. And sometimes I want to write functions that don't support everything that this data structure can do, but only some specific case. And I want to give this specific case a name because I don't want to always write down the complete definition for the type of my data structure, but I want to use some form of name that a programmer that is familiar with the problem domain of my code can easier understand. And for that I can make a type alias, and I define that my hand is just a list of cards. So I can again define this function, hand to integer, and now my values are a bit different. Is this correct? Yes. Again, it is correct. This is not really good. I would like to show some errors at some point to show that this type system really type checks really rigorously and tries to keep you from making errors. But I hope we will come to that as the functions get more complicated.
Ganz kurze Frage, kannst du mal zur Seite gehen, damit man den Code sehen kann?
Oh.
Danke.
Yes, of course. Standing in the way. Okay. Up to this point, everyone's still following. I don't really know when I started being interested in Haskell. Even very simple things seem very complicated to me, so I try to go as slowly as possible. I hope I'm not boring anyone. Okay, so this is a little bit more general, but really what we are doing here, the second function, Handwert, is again very, very specific. We go over a generalized list, but it can just work with this one single data type. And in Haskell, we like to generalize functions so that they can work with as much different data types as possible, but still work very correctly. And one function that is popular in Haskell and is also popular in Perl is map. We all know map. Map is awesome. So we define map. And at first we might not know what to write here, because the first argument of map is, of course, a function. A lambda, some function that I give this function map to mutate a list. And the way we note this in Haskell is we use parentheses, and inside them we say what this function should look like. And because we don't want to write very specific functions, but the most general map we can think of, we use type variables. So I just say I want function A to B. Yeah. So this is my first argument, function A to B. Now, what does map get in addition? It gets a list, but list is not everything. We defined list in some way polymorphic. We generalized it. So when I have a function A to B, I need a list of A's. And I get a list of B's. So again, we now look at what different cases of values can we get. Well, the most basic case is the list that map gets is empty. In this case, the first argument, the function, is really uninteresting because we don't really need to evaluate that function for an empty list. So I just write a placeholder, which is an underscore, and the empty list is of course nil. And it returns again an empty list. The next case for a map is I have something which I call x, cons x, and the rest of some x's. And this is not quite correct. I need the function first. And now what do I return? Well, I return a cons with the f of x and a map f of x's. And this is correct, great. Does everyone understand what's going on in this function? Do we have questions right now? Is something not really clear? If nobody asks, I just move on. The next thing that we need to evaluate our hand with more generalized functions would be to reduce the list of numbers into some form of sum. We can do this several different ways. I have seen in the Perl 6 talk it was called reduce, so I reduce a list down to one value. In Haskell we can call this a fold. The intuition for this name is that I start to fold down a list until it's just one element. And with fold we go one level more complex. What do we need? We need a function that takes some A and some B and gives back an A. We will see why this is in a moment. Then we need some element to start with. We need to work correctly with empty lists. We need some way of neutral element for our fold, which would be an A. And then we get a list of B's, and we get an A back. Trust me, it's really so. Did I make an error? No, it's correct. So, our kind of fold, first thing fold gets its function, and again I want to use the first case to define is the base case for an empty list, and actually the function is not interesting for that. I just take the neutral element, which is the second argument, and the empty list, and just return x. So when fold gets an empty list, it just returns the neutral element that I gave the function. The second thing is, well, now I am interested in the function, and I'm interested in the neutral element that I got, and the const case y and y's, because I already used x and I need everything. So what do I do now with all of this? I have all my arguments, and well, of course, at some point I want to apply f to x and y. This I already know, and this function takes an A, x is of type A, it takes a B, y is of type B, this function should work. In fact, this should also even type check, even though this is not what we want. No, it doesn't type check, fine. Define but not, okay, this is just a warning. So it's boring, but my compiler told me that I defined a variable that I didn't use, and all the time I do that, my compiler suspects there's something wrong with what I did. The compiler yells louder, not in this barely seeable color, but in a bright red when I do something that actually not works. Programming Haskell has much to do with being yelled at by your compiler, which is a good thing. And it is a good thing because the compiler catches errors that usually you would need to write tests to find. We will see that in a moment. What do I need to actually make this function work? My compiler already told me I've defined a variable and don't use it. So, of course, I don't want just to work on the first element of the list, but I need to work on further elements of the list, which, as always in pure functional languages, involves recursion. We don't have for loops and while loops. We don't get those fancy things. We do everything recursively, which is okay because our compiler knows that and optimizes recursion so that it is of adequate performance. And so I already said the return value of this function f returns an A. Well, our fold expects an A. So doing recursion, I have my value A. I have the function that I need for fold, which is just f, and I actually have a rest of a working list. So maybe, so it's not so far down. I think this should be better readable. Now I can return, not return, now I can define a function which sums up lists. And this I can do in a sum function. Well, sums of arbitrary data doesn't really work. I have not defined a type class yet for generalized numerals. So I say explicitly, I have an integer. My Vim knows more than my Haskell actually knows. So I just want these very basic data types. So yes, and how would I now go and write this function? Well, I can use fold for that. That's why I just defined fold. And how this works is basically I give fold, and I give fold a function. The reduced function for sums would be the plus. Operators in Haskell are just ordinary functions which are used with characters other than alphanumerical. And to use a function, to use an operator as a normal function, I just put it in parentheses. And whenever I just write a function and as an argument of another function, it not tries to evaluate that second function, but just gives it as an argument to the first. This all higher order thing is really at the forefront of what Haskell tries to do with its syntax. And I need my neutral element, which is a 0. And one might now see, well, I didn't really touch the list in any way. That's because in Haskell we get lambdas and closures basically for free. I have my function fold, which usually expects 3 arguments, a function, a neutral element, and a list. I now gave fold a function and a neutral element. So when I do that, fold basically returns a function from a list to a result value, because fold still expects 1 additional argument. And this should actually work. Let's see. Yes, it does. It's a nice behaved compiler we have today. So we reload this thing, and now we could calculate the value of our hand by doing something like sum map card value, and what did I call my list? I think I called it. Didn't I? Ah, it didn't because I reloaded it. Yeah, that's not. Let's define it here so I don't have to type that every time I. Okay. What does it say there? Yeah, there's no signature. I trust your compiler, you will figure the signature out. So yes. And now it doesn't work. This is interesting. Okay. This is not the correct data type. This is the old list we defined, and not the new generalized list. We can see this when we give the type of the function hand, which has the type uppercase hand hyphen. This is not what we want. We had another type, which is here, which is constructed a little bit differently. So just when we reload, now it is of the correct type, and since it is of the correct type, this works. Nice. How many time have I left? Oh, okay. I won't go through everything, but one really neat thing I wanted to show, which is function composition and how function composition is actually type check. I think this makes a nice enough point. What?
First character of the result is not shown on the screen, so we can see anything.
Oh, okay. You don't see the result value. How can I? There it comes. There it is. We now see it's an 8. It's actually an 8. It's great that you don't just take my word for this. Yeah, I'm slower than I want to. One thing that I really want to show is function composition. And we define function composition exactly how you might remember in your nightmarish flashbacks to your math classes that you might have took. There's this little circle which composes two different functions, and so how do we that in this language? Well, what we basically want to do is to define function composition, which we define as just this dot, as a function f and function g and an argument x, and we just want to say, okay, f gets as an argument the result of g of x, which is really trivial, and the thing how we define this is again with some sort of type variables to be as general about this as possible. So let's say f is some arbitrary function from a to b. G then has to return the value b, but it has to return the value a. So f understands the return value of g. So g can get some arbitrary value c, but it has to return a value of type a. And so for g to understand x and to work on x, we need a value of type c and get a return value of type a. It's simple. It really is. I don't know, but when I don't get any reaction from you, I don't really know if this is interesting, if this is understood or not. So if you can't follow what I'm doing here, if I'm not expressing myself well, just tell me. And then I want to go and define my sum value now in a different way. I want to say, okay, the value of my hand again. I can define as the composed functions of sum and map so this works, and just no, it doesn't work. This is good. Why didn't it work? I get nice error messages, and actually, this is good. Okay, I made a mistake. Have you spotted the mistake? Is this an error that you could have made? It's actually an error that I made, and what the actually readable error message on the bottom says that I get the result value b, but my function expects the result value of a, and what I actually did wrong is this. And now everything works. And don't be surprised if you can't really quite understand the intricacies of why this didn't work. Just be interested in the fact that I missed it, but my compiler didn't. And this is the point I'm trying to make. All these arrows and type values in something, you might not have a working intuition for this, because maybe this is something that you are not used to. But our intuition is something that we can train, and this is something that you can get used to. I got used to it, and so can you. But the point I'm trying to make is that these types help us catch really stupid mistakes. And as programmers, we always make stupid mistakes. I do them all the time, and I'm sure everyone is basically the same. Maybe someone who is a little bit better at programming than me makes less mistakes, but he still makes mistakes. And this is why I'm interested in these kinds of type systems, because the compiler finds mistakes without running software tests. Software tests are great. A good test suite is awesome, and I want test suits because in more primitive type systems like Haskell's, I can't express everything that I want to test. But I can express a hell of a lot more than in most other languages. And everything I can check with my type system is a complete check. When I write a software test, what I actually do is I find one value or a set of values for which my program is correct for the purpose of this test. When I check something in my type system and I have a well-implemented type system, then this type system expresses some kind of restriction, and I have a check for every single value that I have. Again, I can't implement every check conceivable in Haskell's type system. Haskell's type system is actually by far not as complicated as some people might want you to think. Mostly people tell you that Haskell is too complicated for you because they're not able to implement these type systems in their compilers. But these things exist, they're interesting, and they can help you write better code. Now, another thing that some of you might be thinking right now, why do I need to bother with this? My code runs fine. So did the people that made Mt. Gox. Until people broke Mt. Gox and stole a few thousand bitcoins, I think. My time is up. So, any last question before I'm run from stage? Anyone interested in anything? No.
do your last slide or something. Just finish up with your last.
Okay. I think I just made my last statement. So I would like to thank you for your attention, and if anyone has any questions, I wrote a bunch of links and collected them for the booklet you got. If you want to ask me any questions, if you bother talking to me, I can be found for the rest of the workshop somewhere around here. Just talk to me. I like to talk very long and very in depth about these things. Thank you.